So, good evening and welcome to the 2015 Darwin College Lectures, which this year are on the broad theme of development. And I'd like to welcome everyone here in the Lady Mitchell Hall, people in the overflow halls who are viewing on the video link, and also the many, many thousands of people around the world who watch these lectures later on. They are freely available on the web. Darwin College is 50 years old, founded as the first college in the University of Cambridge exclusively for graduate students, and moreover, the first mixed college. From a small beginning, we are now amongst the largest college, with an alumni body encompassing every subject and spread right around the world. That's a very real example of successful academic development. The third lecturer in this, the 30th series of weekly Darwin College lectures, is Professor Richard Ellis. In 1993, after a distinguished career that led him from UCL to Oxford to Durham, he came to Cambridge as Plumian Professor of Astronomy and Experimental Philosophy. Since 1999, he's been the Steele Professor of Astronomy at Caltech, the California Institute of Technology. If we go back many centuries, Galileo's Accademia dei Lincei was the Academy of the Lynxes, the far-sighted ones. And Richard Ellis today is at the forefront of Galileo's far-sighted successors. Galileo's telescope had a 37mm objective. Richard's has, I understand, a 30-meter mirror. That's quite some advance. He looks to the very edge. He has brought major advances in understanding why galaxies are grouped into the Hubble sequence, and for using gravitational lensing to find some of the most distant objects in the universe. Now, Richard Ellis has two rather nice connections with Darwin College. Firstly, he was awarded the highest honour of the Royal Astronomical Society, their gold medal, in 2011, an honour in which he was followed the following year by our own fellow, Professor Andrew Fabian. Secondly, his Cambridge chair, the Plumian Professorship, was once held by Professor Sir George Darwin, whose house forms the core of Darwin College. Sir George helped advance understanding of the moon and the birth of the solar system. Richard Ellis looks to the very birth of the universe, but he stands in that same tradition. So I'm sure George Darwin would much approve of tonight's speaker. So may I very warmly welcome Richard Ellis to speak on the development of galaxies.
Thank you. Thank you very much for that kind introduction. Good evening, everybody. I'm going to talk about time travel. It's an ancient dream, I think, that we might be able to travel back in time. Everybody has their own personal adventure. Maybe you'd like to go and interview William Shakespeare. I'd like to go back and see the pyramids being constructed in real time, rather than have to speculate how those magnificent structures were made. Astronomers are unique as scientists in being able to travel back in time. When we look at the sun, we see the sun as it was just over 8 minutes ago. That's the light travel time from the sun to the Earth. When we look at the nearest star, we're looking back to see that star as it was 4 years ago. That's the light travel time from the nearest star to the solar system. But the situation changes dramatically when we use a very big and powerful telescope. This is the deepest image we currently have from the Hubble Space Telescope. It's called the ultra-deep field. It represents an area about the 1/10 of the diameter of the full moon. And it represents a collected exposure of over a week of solid observing time with the Hubble Space Telescope. There are about 2,000 galaxies in this very, very small field of view. And the ones colored in these squares here represent some of the most distant objects that we currently know. We're seeing these galaxies not as they were thousands of years ago, or even millions of years ago, but 13.5 billion years ago. Now, the solar system is about 4.6 billion years old. The universe itself, we believe, is 13.8 billion years old. So we're looking back about 97% of the way back to the beginning. So encapsulated in this image is a time tunnel, a tunnel that enables us to attempt to piece together the evolutionary history of the universe over a very, very large fraction of its total age. And so in thinking about development, my task has two rather different themes, both involving the word development. One is the obvious challenge of piecing together the development of galaxies from their birth to the wonderful, magnificent structures that we see around us in the universe today. So that's development of galaxies. The other is the development of the subject. And as you'll see, progress has been very dramatic in the last 10 to 15 years through the development of technologies and clever ideas that have enabled us to advance the subject empirically. And the challenge will be to piece this together into a coherent picture of the evolution of the universe and also, of course, our own place within it. So where better to start than our own galaxy? So the Milky Way is our own galaxy. The Sun is one of 100 billion stars or so sitting in the Milky Way. And the first person in recorded history to get a grasp of the significance of the Milky Way was Thomas Wright of Durham. And in 1750, he published this original theory of the universe, where he successfully, up to a point, realized that the band of light that we see across the sky is, in fact, myriads of stars, the Sun being within that system. And of course, when you look along this band of stars, you see a much larger proportion of stars than if you look at right angles to that band. He, as so often with philosophers, he was a landscape architect. He didn't, of course, have any training as an astronomer, but as often with philosophers, he embellished his ideas, and if he'd have stopped at this particular point, perhaps he might have been more famous than he actually is. He then went on and said, well, maybe it's not a plane, maybe it's a spherical shell. And then he got very excited, and he said at the center of this spherical shell is a supreme being. And so at this point, you know, people started to lose interest in Thomas Wright. But the idea is very clearly there, and you can see this in this very nice illustration. Somebody who's much closer to a modern astronomer, where really one can celebrate his achievements in the context of galaxies, is William Herschel. So William Herschel built his own telescopes, many of them. This is the so-called 20-foot telescope. It's actually the length of the tube. The mirror itself was about 18.5 inches across. Amazingly, this telescope operated pretty close to the runway of Terminal 5. And yet he made significant discoveries. And he catalogued a large number of what he called nebulae across the sky. And in 1789, he realized and put forward the idea, largely a conjecture, I think, that some of these nebulae might be systems like the Milky Way, but beyond the confines of the Milky Way. In other words, external Milky Ways. And you can read this here. He says they may also be called Milky Ways by way of distinction. The confusion was that some of these nebulae were inside the Milky Way, but a large fraction of them, it turned out, were outside. So in some sense, William Herschel was the first person to conceive of the idea of external systems from his own observations. So we come to the 20th century, and Edwin Hubble, whose name, of course, graces the Hubble Space Telescope, demonstrated categorically that a galaxy such as this one, the Andromeda Spiral, lies completely outside the Milky Way. So how did he do this? He measured the period of pulsating stars. So here's his photograph from 1923, and he found a variable star whose period in days, you can see, if you probably can't see this, but this is 10 days, this interval here, so this is about 3 weeks. And you can see these stars are varying in brightness, and that's because they're stable pulsators. Such stars are known in the Milky Way, and the luminosity of these stars correlates very precisely with their period. If you know the period, clearly you can see they're periodic, then you know the luminosity. That's the true intrinsic luminosity of the star. Obviously, you know how bright the star is on the photograph, so hence you can get the distance. And he demonstrated that this wonderful galaxy, which is the nearest galaxy comparable in size to the Milky Way, lies actually far beyond the confines of the Milky Way. So we now see this rich diversity of galaxies, many of whose distances have been determined very precisely from these and other methods. So we see spiral galaxies, like this beautiful example here. The Milky Way is a spiral galaxy also, very similar to this galaxy. You can see it has a central nucleus, lots of blue young stars, and spiral structure, dust lanes, these little black stripes running along here. Contrast that with this elliptical galaxy, where the stars are very red and old. No young stars, no spiral structure, very simple structure purely of stars. And then, as always, there are some galaxies that don't fit into the classification, and these are irregular galaxies, and I'll say a little bit more about those later. Now, the first thing one might want to do in thinking about the physical significance of these different types of galaxies is to understand their three-dimensional structure. And at this point, I'm reminded of an event at the Royal Observatory in Edinburgh, where I think they were having an opening, a public evening where the public could come in and see what was happening at the observatory. And an astronomer took 2 pictures like this to a graphics artist and said he wanted a three-dimensional model of these 2 galaxies made out of plasticine so that he could, have it on the opening of the public visits to the Royal Observatory. And the graphics artist took these photographs and thought about them for a moment, and then about an hour later came back to the astronomer and said, "Do you have a photograph of these objects from a different angle?" So, of course, one of the challenges is how do we determine the true form of these kind of systems? Well, I suppose one could look statistically over the sky, but it turns out we learn much more from the dynamics of the stars and gas in these galaxies. So this leads me to spectroscopy, which is a major theme of tonight's talk. When we get a spectrum of a galaxy, like this particular spiral here, we see strong emission lines from gas, hot gas, heated by the young stars in that galaxy. This line is a hydrogen line, this line is a nitrogen line, and the wavelength of this spectrum line, through the Doppler effect, which I'm sure most of you are familiar with, is giving us the velocity of the gas in that galaxy. So the slit of the spectrograph was placed right along this axis here, so each point here respectively reflects the motion of the gas at that particular point. And you can see it's not a constant. It's got a sort of S-shaped curve here. And the idea is that the center of the galaxy, with respect to the center of the galaxy, one side is receding and the other side is coming towards us. And so the galaxy is a disk that is rotating. And one can measure the velocity of the gas as a function of the position away from the center of the galaxy. And here are we call this the rotation curve of a galaxy, and you can see the galaxies are spinning with a velocity of about 250 to 300 kilometers per second. Our own Milky Way is shown here. Actually, it's rather hard to measure the rotation curve of the Milky Way because, of course, we're sitting within it. One would have to have the distances of any object. Much better to measure an external object. But to the extent that we can measure the rotation of the Milky Way, it's consistent. These galaxies are therefore highly correlated. Their velocities are systematic, and these are what we call disk galaxies, and they rotate about once every 200 million years or so. Now, when I was a postdoc at Durham, one of the surprising results was that the elliptical galaxies are quite different. Now, as the word suggests, elliptical galaxies, not all of them are round, some are elliptical in form, and one might have imagined that just as the sun is slightly flattened because of its rotation, in other words, it bulges at the equator, as does the Earth, one might have imagined that these elliptical galaxies were rotating in order to explain their elliptical shape. It turns out that they're not rotating, they're hardly rotating at all. So this is an elliptical galaxy, and this rather curious looking image is a map made with an instrument actually developed at Oxford that measures the velocity of each point of the stars in this image. And blue would be coming towards us, red would be coming away from us, and you can see it's just basically noise. There's no systematic, it's not as if one side of this galaxy is moving away from us and the other is moving towards us. If the galaxy was rotating in order to explain its shape, then as one went to the more flattened ellipticals, they would be rotating faster. And that's clearly not the case. So the explanation of the shape of these galaxies is really quite remarkable. This galaxy is made up of millions of stars who each have their own independent orbit within that galaxy, randomly. And the shape of the galaxy is the envelope of all of those orbits. So there couldn't be a bigger difference between a spiral galaxy and an elliptical galaxy. They have very different velocities of the stars and gas within them. And that is a very important distinction. So I told you it's an adventure in looking back in time, and I'm going to have to introduce the word redshift, and I will explain this. So astronomers, of course, when one looks deep in the universe, you're looking back in time, as I mentioned. But you're looking back, we can look back so far that over the time travel from, say, a distant galaxy to the Earth, the universe itself has evolved. So one is able not just to look to great distances and back in time, but the expansion of the universe has changed the light that left that galaxy. So you probably know the universe is expanding. It's very dangerous to think of the expansion of the universe as galaxies acting as projectiles in pre-existing space. So often I'm asked, where in the sky was the Big Bang? So the universe is not expanding, the galaxies are not expanding in pre-existing space from a point in the sky. Space itself is expanding. You can think of the galaxies pretty well as being nailed to the spot, and it's the stretching of space predicted by general relativity that explains the expansion of the universe. So concentrate on this particular galaxy here. It is sending a light ray to this galaxy here. And the light ray is blue, but the distance between these two galaxies is so large that the light ray is going to take quite a while to get there. And while it travels there, space has been stretched. And now you go to the top plot, and the universe has evolved. So when the light ray finally arrives at that galaxy, might be the Earth, our telescope, the light ray has been stretched, its wavelength is longer, and we call this the redshift, the shift in wavelength from the light emitted from the galaxy to that received at the Earth. Now, the redshift then is a measure of how much the universe has expanded since the galaxy emitted this light ray here. And so we can correlate redshift with what we call look-back time. This is a very useful concept. The look-back time is the time that we are looking back in history. So here we are today, a redshift of 0 is today. If we go back to a redshift of 1, what this means is the universe has doubled in size linearly since the light ray left a galaxy. And we're looking back about 7 billion years or so. If we go to a redshift of 2, the universe has expanded 3 times in size, and we're looking back to when the universe was about 4 billion years old, or about something like about 9 or 10 billion years in look-back time. So I'll keep referring to look-back time and redshift so that you don't get confused. If you prefer to think in look-back time, remembering that the universe is 13.8 billion years, that's fine. If you can grasp the idea of redshift, I'll be very pleased. So obviously we need to get spectra. In order to measure these redshifts and measure how far back in time we're looking, we need to time slice the universe in different redshift bins. And so in order to do that, we need to measure this wavelength shift. And now, taking a picture of a galaxy is one thing, but getting a spectrum of a galaxy, one has to break the light into its spectral properties. And of course, that takes a lot more observing time. So, for example, a very faint galaxy might take half a night of exposure on the largest telescope to clinch its redshift. Clearly, astronomers are competitive individuals. We don't get the telescope entirely to ourselves like William Herschel did. We have to compete. We might get 3 or 4 nights a year or 6 nights, something like that, on a large telescope. So if it's going to take half a night to measure a redshift, we're not going to make much progress in getting large statistical samples. So the first technical development, if you like, bearing in mind the theme of development that I want to introduce, is what we call multi-object spectroscopy. So the idea here is that a telescope has a field of view on the sky. You saw that picture. There were many galaxies within a field of view on the sky. The field of view is covered by this brass plate, which was placed at the focus of the telescope. And holes are drilled in this brass plate at the precise location of 50 galaxies. And this rather Heath Robinson-looking apparatus takes 50 optical fibers, fiber optic cables, and each fiber is placed within one of these holes. This is an excellent job for a graduate student. And each fiber has a number, and each hole has a number, and heaven forbid if you should lose that piece of paper that tells you, you know. So we began this in the 80s with the Anglo-Australian telescope, and it was a big hit. Imagine now measuring the spectra of 50 galaxies simultaneously. That's a huge step forward. In a way, it's like having a telescope 50 times more powerful. But really, we realized that this manual mode was not really the end point of this development. So a few years later, we developed an automated way, a robotic system, where a robot comes along, it's an electromagnet, it picks up a fiber, say from the periphery here, and moves it to the precise position of a galaxy. The light comes down from above from the sky. It enters one of these little units, which has a tiny right-angle prism in it, which deflects the light into here. And then all of these fibers are gathered together and fed into a spectrograph. Largely as a press PR stunt, we got this robot to make a map of Australia, to which the response was always, what about Tasmania? And anyway, this led us up to 100 objects, and then this culminated in one of, I think, Britain's biggest achievements in this area, which was a much more advanced robot which was able to move 400. And this was called the 2-degree field facility, and here it is on the prime focus of a telescope. And when I was in Cambridge, many of us in Cambridge with our colleagues in Australia, we did a survey of 250,000 galaxies with this instrument. Now, this robot moves these fibers one by one, and so it's still not optimal because it took 10 minutes to position 400 galaxies. The way this was dealt with this instrument was that we had a sister equivalent instrument at the bottom here. So while we were exposing with one set of 400 fibers, the robot was positioning the next set, and then a massive tumbling took place so that the one that had been predetermined, positions had been predetermined, flipped up to here, and then very little observing time was lost. Well, I'm going to bring you up to date. We're now building an instrument that will do this for 2,400 galaxies at a time. And we're planning with the Japanese 8.2 meter telescope to do a survey of 10 million galaxies. And we've broken this barrier of moving the fibers one by one with a very clever idea that our colleagues at the Jet Propulsion Lab came up with. So we have the fiber runs through a little unit like this, which is about the size of my little finger. And viewed from above, there are two motors, two small piezoelectric motors, one here and one here. And via this eccentrically mounted two-motor system, if the fiber tip is here, you can see we can patrol any area enclosed within this dotted circle. So we line them up, and then we insert them in here, and we build up 2,400 of these, and they're all moving independently. And it only takes 40 seconds to configure 2,400 galaxies. So this instrument will be ready in 2017, and it will do a 300-night survey of distant galaxies with this technique. So this is where we were with the older instruments. This is really the culmination of the surveys my colleagues and I did at Durham. And what you see here is, and this was with the Anglo-Australian telescope, what you see now here is redshift. Conveniently, for those who don't like redshift, this is the look-back time in billions of years. So this is about halfway back to the Big Bang. And each point here is a galaxy. And I've plotted the luminosity, because galaxies don't all have the same luminosity. Some are feeble and some are luminous. And so as you go to fainter surveys, certainly you look deeper in the universe. But you also pick up feeble objects that are nearby. So I think you're familiar with this. If you go out into the street and you look at lights, you can't really judge how far away they are. It could be a headlight a long way away. It could be, a feeble lamp pretty close by. Galaxies are very much the same. As we probe deeper and measure their distances, or redshifts, you can see that we uncover feeble objects as well as more distant objects. So it's not a very efficient way of probing to the very far edges of the universe. Just going deeper, going to fainter galaxies is not necessarily optimal. So one of my colleagues at Caltech, Chuck Steidel, came up with a very clever way of pre-screening which galaxies are truly distant. And the idea is that hydrogen, the most abundant element in the universe, has a very strong absorbing effect at ultraviolet wavelengths, so that the spectrum of a galaxy is curtailed at a wavelength which is known. It's in the ultraviolet. And so with a clever use of three filters, a red filter, a green filter, and an ultraviolet filter, you can find in advance which galaxies are truly distant. So let me explain. Here's a galaxy that's visible in the red filter, is visible in the green filter, and it's visible in the ultraviolet filter. So it's not so distant that this hydrogen absorption has taken effect. Here's a galaxy that's visible in the red filter, the green filter, and it disappears in the ultraviolet filter. So what Steidel did was to take huge areas of sky and just find these objects. They're called dropouts, the idea being that they drop out of view in the shorter wavelength filter. And I remember this very well in the 90s. It was a breakthrough. Suddenly, we went from, what had taken me a huge amount of effort with the telescopes that were available at the time to a redshift of 1. He was able to go out to a redshift of 3. So Hubble Space Telescope was launched in 1990, repaired in 1993. And now that we have the distances to populations of galaxies out to redshifts of 3 and beyond, one can get the first simple view of the evolution of morphology of galaxies in the universe. So here are some familiar galaxies. Here's a classical elliptical galaxy nearby, and here's a very nice spiral galaxy. So the surveys that I did probed to a redshift of 1. That corresponds to when the universe was just under half its present age, 5 billion years. Here are some galaxies whose redshifts are known. And you can see these two look pretty similar to this elliptical galaxy. Here are two objects that have nuclei. There's a sort of spiral structure. Maybe it's not so beautifully delineated. It looks maybe a little immature, but one could argue that these objects are already beginning to form a spiral structure. And then here are two irregular galaxies. I showed you that there are irregular galaxies today. It turns out there are many more irregular galaxies at this time than in the present universe. But if you go to the highest redshifts of 3, when the universe was only 2 to 3 billion years old, the galaxies bear no relation to the galaxies that we see today. There are no spirals, no obvious ellipticals. Many of them are multiple, as if they're merging and assembling from smaller units. Let's have a zoom in on these. They're physically very small. They're 10 times smaller than the galaxies we see today, like the Milky Way, yet they're forming stars prodigiously. So the Milky Way is forming stars at the rate of about 1 to 2 suns per year. These galaxies are forming stars 10 times faster. So clearly they're in a very active, one might even say adolescent phase. And then there are these multiple components. What does this mean? Why are these merging and assembling? Are they merging systems that are building up to larger systems from smaller units? Now, Hubble, of course, gave us this wonderful view of the distant universe by virtue of the fact that it's above the Earth's atmosphere. So there it is, a few hundred kilometers up. It goes round once just over an hour or so all the time, and it's been a phenomenal success. And of course, one of the reasons why it's been so successful is it is above the Earth's atmosphere, and so it's unaffected by the blurring and the twinkling of starlight and galaxy light that we see from the ground. I now come to the second technical development, and that is a technique that we call adaptive optics. And adaptive optics has revolutionized our way of looking at these galaxies with our ground-based telescopes, complementing very nicely what we can do with Hubble. So these are the twin Keck telescopes, the 10-meter telescopes on Mauna Kea in Hawaii. And what you're seeing here is 2 lasers being launched into the sky. These are sodium lasers, 10 watts or so, very powerful, and they illuminate a layer of sodium atoms high up, tens of kilometers up in the Earth's atmosphere. Sodium gets deposited in the Earth's atmosphere from meteors burning up, and so when the laser shines on these sodium atoms, of course the laser beam is very, very sharp, it creates an artificial star. And that artificial star is then monitored as its light comes through the atmosphere. It's a very bright artificial star, and we can actually monitor with an instrument we call a wavefront sensor the corrugations in the incoming light as it comes through the atmosphere and reaches our telescope. And this signal, this distortion in the incoming beam, is used in a control system to adjust a deformable mirror. So these are very expensive pieces of equipment. A mirror, a reflecting mirror, which has many, many individual elements, each of which can be activated according to the signal that's received from this wavefront sensor. The biggest deformable mirrors now have 3,000 components, and we have one at the Palomar Observatory. The one at Keck is very powerful. And with this adaptive mirror, we can then correct the incoming beam from our celestial target, say the faint galaxy, in sync with the signal that we see from the laser guide star. So we create images and spectra that are better than those from the Hubble Space Telescope. You look somewhat in disbelief. We couldn't possibly outpace the Hubble Space Telescope. This is a picture of 2 pictures of Neptune taken with a Keck telescope under normal, pretty good conditions. And you can see there are probably some features here. This is on the same nights with the adaptive optics at the Keck telescope switched on. And these are infrared images. Neptune has a ring. You can see it's very, very sharp, just like Saturn. These are clouds of methane in the atmosphere of Neptune. And you can see that these are taken on different nights. You can see the weather developing on Neptune. Not a hope of doing that without adaptive optics. And these images are sharper than those that one could get from the Hubble Space Telescope. This is the center of our galaxy, the center of the Milky Way. It's a very, very rich area where there are lots of stars. This is in the southern sky, not easy to see with the Keck telescope, but in June and July it can be seen and studied. And if this is what we see without adaptive optics, this is what we see with adaptive optics. And of course, one can measure the positions of these stars in the center of the galaxy very, very accurately. One wouldn't be able to do that without adaptive optics. And Andrea Gertz, who's a professor at the UC Los Angeles, during her career has measured very carefully the motions of all of these stars and their orbits. She's followed their orbits and demonstrated that there is a massive black hole in the center of the galaxy. So what have I done with adaptive optics? So what we've been looking at is distant galaxies to see whether there's the beginning of rotation. So here's a very distant object, and you can see, again, one side of the galaxy is moving away from us, and the other side is coming towards us. And this is a very nice rotation curve. Now, the velocities are not as high. If you remember, the Milky Way was rotating at about 220 kilometers per second. This galaxy is rotating about 45 kilometers per second. But this is at a redshift of 3, when the universe was only 2 billion years old. Now, there is one big difference, which gives us the confidence that this is an object that will become a spiral galaxy, but it's not yet completely settled down. And that's that there's a lot of motion that is random, what we would call the turbulent motion of the gas. So it's as if the disk of this galaxy is somewhat still thick and settling down. It will eventually settle down and become a tightly rotating system. But it is still a very, very small system, and so it still has to grow. Likewise, we can track the history of the elliptical galaxies, and they're growing too. So this montage from Hubble, where we have the redshifts of all these objects, shows what I've done here is at each redshift, I've collected a set of galaxies, and I've made the images the same physical size in real units. So you can see, as we come down to the present day, the galaxies are they're very similar, actually, morphologically, but they're just growing in size. So the evolutionary history of spirals and ellipticals seems relatively straightforward. The spirals are slowly settling down into disks that are rotating. The ellipticals are growing in size, but maintaining their morphological forms. Now, there is a danger in this kind of simplistic view that galaxies may somehow migrate from one morphology to the other, and that's always a challenge in making a general picture. So the question that arises now is, what is the physical mechanism by which these galaxies grow? Both the ellipticals and the spirals are very small at early times, but by the present day they're very much larger. So there are three ways in which, or three physical mechanisms that are important in the growth of galaxies. One is the gravitational attraction of gas onto galaxies. Now, galaxies are formed of gas clouds. The universe contains a lot of gas outside galaxies. So in between galaxies, there's material. We call it the intergalactic gas. It's very tenuous, a very low density, but the universe is a very big place. So there's a lot of gas out there. And of course, it's gravitationally attracted. So that gas can fall in and it will be pristine, by which I mean it hasn't been polluted by star formation. So it's really largely hydrogen and helium the atoms that formed in the Big Bang. Galaxies can merge. We saw in those Hubble pictures that galaxies are close together. So a galaxy can grow by meeting another galaxy and merging and building a bigger system. So theorists calculated many years ago that if these two methods were the only way in which galaxies grow, they would grow much faster than we observe. So there must be some regulating mechanism that slows this process down so that it's compatible with observations. And galaxies can be pretty energetic places. So stars, when they die, they explode briefly in a huge release of energy. That creates velocities for the gas. It can even send the gas out of the galaxy. Black holes in the center of galaxies, just like the one I showed you that we believe is at the center of the Milky Way, when they're active, they can expel gas and heat it up. And so the balance between these two processes, particularly the inflowing gas that's pristine and the outflowing gas, which is of course processed because it's expelled from stars, which are nuclear factories that are converting hydrogen and helium into heavy element, gets us into the very interesting topic of the chemistry and the evolving chemistry of galaxies. Now, we see today that the chemistry of a galaxy varies with position. So if we look at a big spiral galaxy, for instance, the oxygen abundance of the gas is higher in the center than outside. Whereas if the galaxy is merging, that gradient, that chemical gradient across the galaxy is pretty small. And likewise, we expect that if there are big outflows of hot gas, then this will erase these chemical gradients. So the key measurement really that will determine these competition between these outflowing feedback processes and these infalling cold gas is to measure these chemical gradients. Now that's a pretty big challenge. So I come to, there's a movie, I must have the movie. So this is a movie simulation by one of my colleagues at Caltech of two galaxies. You're looking at the gas, and these two galaxies are spirals. They have disks, and the first thing you see when they come close to each other is that the disk is very fragile. The disk gets disrupted very easily. The gas can get expelled into new orbits. It can be randomized, and of course it can be heated up as well. And then, but at the centers of these galaxies, there are two small black holes, and these galaxies merge and create a much larger black hole. And that black hole has a huge amount of energy, and it can expel, the feedback from that black hole can expel the gas out of that galaxy entirely. So clearly this process of outflowing gas is very, very important in understanding the assembly history of these objects and how they get bigger with time. So the third development is gravitational lensing. This is a very important tool now for astronomy. No prizes guessing who this is, but of course he predicted that light would be bent by massive objects. And this was verified by another Plumian professor, Arthur Eddington, here at Cambridge at an eclipse in 1919. We're coming up to the 100th anniversary of this famous eclipse, where he took photographs that showed that at the time of an eclipse, starlight is deflected gravitationally by the gravitational field of the sun. And arguably this really catapulted Einstein to fame and this gravitational lensing technique. A few years ago, my wife gave me an Einstein calendar. You know, it was one where, you know, every month Einstein is doing something different. You know, it was Einstein against the blackboard, and then, you know, Einstein on a bicycle. And by the time we got to April, I realized Einstein only had one suit. Never seen him in anything other than this one suit. So here's the size of a galaxy at a high redshift. And you've already seen adaptive optics. So we resolve the galaxy. This is the size of the galaxy. Here's how well we do with adaptive optics. Gravitational lensing is like a natural telescope. It stretches the galaxy on the sky. It magnifies it. Think of it as a magnifying glass, a natural magnifying glass. So we get an additional boost in the magnifying power of our telescope. It can be as much as a factor of 10 or so. So my students and I have been working quite hard to look at these gravitationally lensed objects to measure the chemical gradients. And sure enough, we've succeeded in measuring these gradients. So here is one of these distorted images. Here it is in hydrogen. Here it is in oxygen. Here it is in nitrogen. And these gradients are very, very much steeper than the gradients that we see in nearby systems. So we've done about 15 objects now. We're slowly building up a picture of how these chemical gradients are growing with time. It's very challenging work. But to the extent that we've made progress, we're seeing broadly what our theoretical colleagues predict. The theorists are always ahead of the observers. It's extraordinarily depressing, but we just have to live with it. If we verify their theory, of course they're very pleased. If we disprove it, they don't believe the observations. So anyway, here's the growth that was predicted, and you can see to the extent that we have data, we verify it. For the mergers, the gradients are erased, and indeed, that's more or less what we see. So time is running on. I want to get to the last part of the talk, which is the very birth of galaxies. And I think this is a very exciting area at the moment. Here's an artist's impression of the history of the universe, starting with the Big Bang. And about 350,000 years after the Big Bang, the universe expands and cools. The hydrogen atom forms for the first time. The universe is dark. There are no stars or galaxies. There's dark matter, which I haven't had time to talk about, but the dark matter we think is not the stuff that makes up you and me, but is a different particle that has already detached from the expansion of the universe. And it has mass, and so it can cluster and act as little nuggets that the hydrogen atoms now fall into. And eventually these hydrogen clouds collapse, they get hot at the center, they ignite nuclear fusion, and so we see what we call cosmic dawn, the very first moment of starlight in the universe. Now these stars have only hydrogen and helium. They're very, very hot, and they emit copious amounts of ultraviolet light, which breaks apart the hydrogen back into a proton and an electron. The energy from these stars is so intense, it ionizes the hydrogen again. We call this reionization. And so this is shown here. These ionized bubbles eventually overlap, and the universe becomes completely ionized, which we've known since the 1960s, that the universe is ionized in deep space today. So I like this slide very much. It's produced by Professor Avi Loeb. He's at a very minor community college on the East Coast. You probably haven't heard of it. But there's a simulation of this process, and I like this very much. So what you're seeing is the dark ages in black, where the hydrogen is completely neutral, and these blue regions are the ionized bubbles. And this is a cube where the expansion of the universe has been taken out so that it's more easy to see. And this cube, you'll see, as these ionized regions get larger, they eventually connect, like Swiss cheese. And so one starts to see the entire network connecting, and eventually the universe is completely ionized. The red regions represent the boundaries between the neutral and the ionized regions. So it's a rather slow movie, but this is 200 million years. And it's produced by Tom Abell and his colleagues at Stanford. So can we see this moment? Wouldn't it be amazing to go back and witness directly cosmic dawn, the switching on of starlight in the universe? So a few years ago, my students and I thought, well, this is something that we should push Keck. A big telescope like Keck, of course, there's no point doing small projects on it. We should do something very ambitious. So we started using the Hubble images to target extraordinarily faint galaxies and doing 2 night exposures. And we got to a redshift of 6, which is when the universe is about 1 billion years old, about 7%. And what we see is this glowing line of hydrogen. So what you're seeing here in black is an ultraviolet line of hydrogen called Lyman alpha, and it's been redshifted by these numbers, redshift of 6, into the optical and far red region of the spectrum. These annoying stripes are hydroxyl lines in the Earth's atmosphere, which of course one has to live with. Now this hydrogen line is very, very common. It's the most common line in hydrogen in a galaxy. And the reason is that if the galaxy is forming stars, the stars heat up the hydrogen gas and it glows in this line. So for atomic physicists, it's the n equals 2 to n equals 1 transition in hydrogen. It's the most common line, but it's normally in the ultraviolet. Unfortunately, or perhaps fortunately, this line is very fragile. If this photon at this wavelength encounters a neutral hydrogen atom, it gets scattered. So if you're sitting in the dark ages, this hydrogen line will not travel very far. If you're sitting in one of those ionized blue bubbles, this line will escape. And by the time it reaches the edge of the ionized bubble, it's no longer in resonance with the hydrogen, and so it escapes. So this is a complex idea, so I have a little analogy for you. It's very much a Los Angeles analogy, I'm afraid. Basically, you're sitting on a bridge looking down the freeway, and you're looking back in time. Every car is a galaxy, and every headlight is this glowing hydrogen line. And as you go into the dark ages, the cars are there, but the headlights basically are scattered. The light from the headlights is being scattered by the neutral gas, which is a fog. So it's a very simple test. We should see the visibility of this line going down as we enter the dark ages. And sure enough, that's essentially what we've been able to see. So here we were at a redshift of 6. Half the galaxies show this hydrogen line. By the time we get to a redshift of 8, none of them do. So we're pretty sure that we've nailed when the Dark Ages ended. It was pretty well about 800 million years after the Big Bang. So how much further back can we look? So back to this very deep Hubble image. Here are the most distant objects, incredibly faint. They're at redshifts up to 12 or so. So over the last 2 years now, various groups have charted the number of these galaxies as we go back to these high redshifts. And you can see it's more or less continually declining. And so we've pushed back to when the universe was 350 million years old, and there's still shining galaxies out there. So sadly, we're not quite there. We've not yet quite reached cosmic dawn. But the future, I think, is pretty exciting, and I'm talking now only about 2 to 3 years initially, and then finally with these giant telescopes. So this year saw completion of an amazing instrument in Chile. It's a global instrument, involves Europe, United States, and Japan, called ALMA, the Atacama Large Millimeter Array. It is a network of telescopes. Each one is a pretty significant telescope. It's an interferometer that gives us exquisite resolution. So it gives us Hubble resolution at millimeter wavelengths. And that millimeter wavelengths will allow us to trace the chemistry of the gas in these distant galaxies. So that's a very immediate and exciting opportunity. In 2018, we will launch the James Webb Space Telescope, which is the successor to Hubble. And one of the goals of the James Webb Space Telescope is to search for these earlier periods. It has a spectrograph on it called NIRSPEC. It's already being built and delivered that will measure the composition of these early galaxies. Here's a galaxy of the kind that we're just barely detecting with Hubble, and we'll be able to measure the oxygen lines in these galaxies. So the ultimate test of a first-generation galaxy would be, of course, no heavy elements. So this is, I think, a very exciting opportunity too. And then finally, Mary mentioned the 30-meter telescope. I moved to California largely to get involved in this. It's turned out to be a much bigger adventure than I ever imagined. Initially, it was going to be a partnership between Caltech and the University of California. Then we co-opted Canada and Japan, and now China and India. And I'll leave it to your imagination how interesting it's been to bring together those very diverse communities and agree who builds what and how much observing time everybody gets. But we have achieved that, and we have a partnership that's now cemented. We had our groundbreaking ceremony last October. So this is a telescope that's 3 times the diameter of the Keck telescope. It will be on Mauna Kea, right next to the Keck telescopes. The Europeans, they had to have a bigger one. When I was in Cambridge, Andy Fabian and I would always grumble about how everything had to be bigger in America. But now I've seen it from the other side of the Atlantic. The Europeans had to build a bigger telescope, 39 meters. They originally had a 100-meter telescope. This one's called the extremely large telescope. Their original design was 100 meters, the overwhelmingly large telescope. But seriously, it's going to be fabulous having these 2 telescopes. They're in different hemispheres, and I'm optimistic there will be partnerships between them. One thing they have in common is the mirrors are segmented and made of many small units. And of course, that's been pioneered with the Keck telescope. So TMT will have 492 segments. So that's going to be quite an exciting development. So thank you very much for listening. In answer to the question of whether this is all worth it, one goes back to Edwin Hubble. Not a very popular man with his colleagues. He went back, he was at Oxford, he was a Rhodes Scholar, he went back to California, and they really disliked his affected Oxford accent. But he was a tremendous promoter of science, and he gave a series of lectures at Yale University in the 1930s, which are written up in a book called The Realm of the Nebulae, which actually has just been reprinted. And there's this lovely quote in that. We search for distant landmarks. The search will continue. The urge is older than history. Thank you very much.
So thank you very much indeed. The Cyclos Galacticus, the Milky Way, has, as we've just seen, has tantalized people since the very beginning of human search for understanding. And perhaps, like some of you, I've been fortunate enough to spend time in the remote parts of the southern hemisphere. You go out on a dark night and look up, and you don't see Arctos, or as we might say, the Great Bear or the Plough, but you see Orion, the Pleiades, and the brilliance of the Milky Way, and the clouds of Magellan. And the challenge to comprehend as you gaze is just overwhelming. So Richard, thank you very much for a marvelous exposition of our continuing quest to see further and farther back. And Galileo's Academy sought to be far-sighted, but could they have ever imagined how far-sighted their heirs would become? I think not. And we shouldn't either forget that the wider impact. Astronomy produces wonderful images and is amazing, but it also helps shape society. St. Paul quotes Phenomena by Aratus, the great astronomical text of that time, as being a formative insight. And later, Galileo's vision similarly transformed society. So I just wonder what wider changes might ensue as we come closer towards understanding the birth of the universe. So thank you very much indeed. Now,